Hello everybody. Today I'm going to talk about this idea of even and odd signal decomposition. So I was reading through my signals book and I ran into this idea that you can break down any signal x of t into the sum of an even and odd signal. So I guess this for me was a reasonable idea, but I didn't really fully understand it. So I did a little bit of extra digging and I thought about two approaches that you can look at this, two different lenses to view this problem. And they were able to convince me, and I hope that these, if there's any confusion on this topic, that these are maybe interesting ways to look at this problem and that they convince you that this idea is true. So the first approach I'm going to take is kind of like a linear algebra approach, and the second approach will be like a basic calc 2 approach. So let's get started. Before I start, I want to make sure that we're fresh on the idea of even and odd signals. Even and odd signals obey this property. For even signals, if we take the reflection of the signal, this is equal to the original signal. So in other words, they're symmetric around the t equals 0 axis. And kind of the opposite for odd signals is that if you take the reflection of them, they're anti-symmetric. So they look the same, but they're flipped, right? So this is important. We're going to use this idea of symmetry in the linear algebra approach to kind of derive these formulas. So in the book, they kind of just gave you these formulas and not much intuition, but what I want to do is I want to kind of come back to these and think about how we can get to these formulas like intuitively. And hopefully they will make a little bit more sense once we come back to them. So I want to begin by thinking about the linear algebra approach. So when I saw this x of t is equal to x of e plus x of o, I kind of thought about this as a projection problem where we can think about x of e and x of o forming some basis of some function space where our signal lives. So we can think about this as being some linear combination of these two basis subspaces, if you will. And I wanted to like be thorough with this, so I mean not so thorough, but I wanted to check that these were orthogonal. So we can be confident that our x of t really can be described by any like linear combination of x of e and x of o, right? So to check this, we need to make sure that they're orthogonal to make sure that they form a basis that can describe x of t. So by taking their inner product, we get this integral here, which is basically like a generalized dot product for functions. And we can utilize this idea of symmetry and anti-symmetry to simplify it and make this inner product pretty easy. So we know that even functions are having this symmetric property and these odd functions having the anti-symmetric property. And when we take the product of these two, our resulting function, which I called here h of x, is actually just going to be an anti-symmetric function. And the implication of this is that when we integrate an anti-symmetric function over symmetric bounds, in other words, if we integrate some function h, which is odd, from negative a to a, that's going to be 0, because you can think about that as being the area under some curve where the area cancels out from negative infinity to 0 and then 0 to infinity. They have the same area but opposite signs, so they're going to be guaranteed to be 0. So cool. What does this tell us? This tells us that x of e and x of o do form some function space where x of t can live. And it is valid to kind of think about this as some sort of projection problem where we can have some arbitrary space that looks like this where x of t can be some vector that is like a linear combination of an even function and an odd function. So in this subspace, something that's going to be very crucial in deriving the formulas is this x of negative t, which I'm calling some sort of reflection operator, where we can basically apply that on a signal and think about what that reflection does in terms of symmetry. So let's get started by kind of thinking about how we can derive this equation for the even component of x of t. So in this formula, what we do is we add the original signal and the reflected signal. So why does that give us the even component? Well, let's think about that for a minute. If we have some even function and we reflect it over the t equals 0 axis, we're going to get something positive, right? But what would happen if there was some component of our signal that was odd? Well, the effect that adding the original signal plus the reflected signal is that any part of that signal that was odd is going to be negative, right? So when we add it, it's going to cancel out. It's going to be like essentially a minus sign. And when we add x of t plus x of negative t, any component that's even will be added. And that's why we have to include this divided by 2 term to ensure that we're not modifying the amplitude of our signal. So just as an example, let's say that we have a pure even function such as a cosine function. If we do cosine plus the reflection of cosine, which will just be cosine since it's even, then we get 2 cosine, and then we divide by 2, and it predicts correctly that the even component of cosine is just cosine. Cool. And we can think about a similar thing for the odd projection, right? If we take our original signal and reflect it, if we subtract, instead of adding, if we subtract the reflected signal, any component that's even will be positive, which will get subtracted off, but any component that was odd will get reflected down, essentially adding a minus sign, and then the double minus sign will give you an addition. So adding the signal to the reflected signal gives you the even components, and subtracting the reflected signal from the original signal gives you the odd components. And then this dividing by 2 is again kind of just for bookkeeping, to make sure that we're not modifying the amplitude of our signal. Cool, so I hope that kind of makes sense how we can get those equations intuitively by thinking about symmetry and the ramifications of adding the reflected signal versus subtracting the reflected signal. So what we can do is just go into doing an example. Let's just decompose this signal t squared plus 3t into even and odd components. So if we apply our formula to get the even component, we're going to do our original signal plus the reflected signal, which is just this here, and divided by 2. And what that gives us is t squared, right? And to get the odd component, we're going to take our original signal, and then we're going to subtract off the reflected signal, and then divide by 2, which gives us 3t. Cool. This should match your intuition, and maybe we might not have even had to plug these into these equations that we developed, because it's almost kind of obvious, right? It's just a polynomial, so we can see the individual terms that are even and odd, but it's good that our expressions match what the intuition is, right? And if we think about this graphically, we have this t squared component, which is the even signal, and then we have this 3t component, which is the odd component, and when you add them up graphically, you get this combined signal t squared plus 3t, which is the exact same as the original signal. Cool. We're going to come back to this idea of it being kind of easy to see even or odd based on the polynomial. We could have even just basically skipped this step, and I could have told you just by looking at this what the even and odd components were. We'll come back to that in a minute. A more interesting and informative example is to try to decompose x of t equals e to the t into even and odd components. This is more informative because e to the t is nor even nor odd entirely, so we'll have components in both subspaces, and it's not obvious from looking at it what those components are. And we can apply our formula here. To get the even part of e to the t, we're going to do e to the t, which is our original signal, and then we're going to add the reflected signal, e to the negative t, and divide by 2. And this is kind of interesting. This, if you don't recall, is the exponential definition for hyperbolic sine. So we can express the even part as hyperbolic sine. Super, super cool. And if we look at the plot, oh, it looks like I switched these up. My apologies. This is actually the definition should be for hyperbolic cosine, as shown here, because hyperbolic cosine is the even component. And looking at the odd signal, this is the definition for hyperbolic sine, which is plotted here. So we can see that the signal e to the t can get decomposed into even and odd functions, and they're kind of cool. They're not so obvious. And if we graphically add up hyperbolic cosine and hyperbolic sine, we can synthesize this original signal again by looking at the odd and even components, which is super cool. All right, so now I'm going to go to like that Calc 2 approach where we saw in this example that it was really easy to get the terms if it's a polynomial. So what did we learn in Calc 2 that allowed us to turn functions into polynomials? Well, nothing more than the Taylor series expansion, right? So what we can do is we can take our original signal e to the t, and we can take the Taylor series expansion of it. And this maybe or may not look familiar, but here is the Taylor's expansion for e to the t, and here are the first few terms. And you'll notice that e to the t has both even and odd components, which makes sense, right? Because from our analysis, we saw that it did have both. So it makes sense that in the Taylor series expansion, we see these even terms, and we also see these odd terms. And this should kind of be a hint of like why we're doing this expansion. What we can do is we can isolate the even components and the odd components by kind of separating out their series and then writing a Taylor series expansion for the even parts and then the odd parts, which is shown here, where we can do the even components and the odd components respectively. And this will just give you the original Taylor series expansion. But what we can do is we can see if we can write these Taylor series expansion as like some function, right? Or better said, we can try to pattern match to see if there is a function that has that Taylor series. And if you haven't guessed it already, this is nothing more than hyperbolic sine and hyperbolic cosine as shown here. So by two different approaches, we were able to see that we were able to decompose e to the t into a sum of even and odd functions. In this case, they were hyperbolic sine and hyperbolic cosine. But I hope that looking at this like kind of linear algebra lens, looking at the projections onto the even and odd subspaces, and also looking at like the Taylor series by seeing like what you know about even and odd in terms of polynomials, I hope that this makes a little bit more sense and it might convince you that this even and odd idea is true. I hope that helped. Thank you.